Welcome to my sleep science channel. Like, subscribe, and tell me where you are watching from. Tonight, we begin a gentle journey into one of the strangest places in the universe. A place where matter is squeezed to unbelievable densities and familiar objects lose their ordinary meaning. We are going to explore what happens inside a neutron star, slowly and carefully, like a quiet bedtime story carried across the stars. If you could travel through space and approach a neutron star, the first thing that might surprise you would not be its appearance, but its size. Despite containing more mass than our sun, a neutron star is only about 20 kilometers across. In everyday terms, that means an object containing the mass of hundreds of thousands of Earths could fit inside an area no larger than a city. Imagine standing on top of a mountain and looking at the lights of a city below. Now imagine shrinking that entire city until it becomes a sphere. That sphere would still be larger than many neutron stars. Such an object would appear almost unreal. Yet neutron stars are very real, and astronomers have discovered thousands of them scattered throughout our galaxy. These extraordinary objects are born from stars much larger than the sun. After spending millions of years producing energy in their cores, those giant stars eventually run out of fuel. What follows is one of the most dramatic events in nature, an explosion so powerful that it briefly outshines entire galaxies. From the remains of that explosion, something remarkably compact and dense can emerge, a neutron star. At first glance, the name itself sounds mysterious. The word neutron refers to one of the tiny particles found inside atoms. In the ordinary world around us, atoms contain protons and neutrons packed together in the center, with electrons moving around them. Everything you touch, from your pillow to your bedroom walls, is made from atoms that contain vast amounts of empty space. If the nucleus of an atom were the size of a marble, the electrons would be far away, leaving enormous gaps in between. Inside a neutron star, those gaps disappear. Matter becomes compressed so intensely that the familiar structure of atoms can no longer survive. The ordinary arrangement that exists everywhere around us is transformed into something far stranger. It is almost as though nature takes all the empty spaces out of matter and presses what remains together with unimaginable force. To understand just how extreme this is, consider a simple teaspoon. On Earth, a teaspoon filled with sugar or water is light enough to hold comfortably. A teaspoon of neutron star material, however, would weigh billions of tons. Such numbers are difficult to visualize, because nothing in daily life offers a comparison. Entire mountains would weigh less than a tiny sample from one of these stars. Yet, despite their incredible density, neutron stars are not giant cosmic monsters wandering through space. From a distance, many appear rather ordinary. Some spin quietly, while others send beams of radiation sweeping across the universe, like the rotating beam of a lighthouse. Certain neutron stars rotate hundreds of times every second, completing more rotations in 1 second than a ceiling fan might make in several minutes. Their surfaces are also incredibly hot. Newly formed neutron stars can reach temperatures of millions of degrees. Over time, they gradually cool, releasing energy into the darkness around them. Even after millions of years, many remain warmer than almost anything we encounter naturally on Earth. One of the reasons neutron stars fascinate scientists is that they push the laws of physics to their limits. Conditions inside them cannot easily be recreated in laboratories. Their interiors contain forms of matter that may exist nowhere else. Some researchers believe strange particles could appear deep within their cores. Others wonder whether the particles themselves might break apart into even smaller components. The truth remains hidden beneath layers of matter compressed beyond imagination. Neutron stars are also connected to some of the greatest mysteries of the cosmos. They help scientists understand gravity, nuclear forces, magnetic fields, and the origins of heavy elements. The gold in jewelry, the platinum used in technology, and many other precious elements may owe their existence to ancient collisions involving neutron stars. In a sense, these distant remnants have helped shape the material world around us. As we continue this quiet exploration, it helps to remember that neutron stars are not exotic ideas invented by science fiction writers. They are real objects, drifting silently through the galaxy. Some spin alone in darkness. Others orbit companion stars. Some remain calm for millions of years, while others release bursts of energy so powerful that they can affect regions far beyond their immediate surroundings. Far away, hidden among billions of stars, these remarkable spheres continue their endless existence. Their interiors remain largely invisible, their deepest secrets locked beneath crushing layers of matter. Yet through observation, mathematics, and careful reasoning, humanity has gradually begun to uncover pieces of their story. And somewhere in the vast silence of space, countless neutron stars continue spinning, cooling, and quietly carrying within them some of the most extraordinary conditions that nature has ever created. When we look up at the night sky, stars appear calm and unchanging. They seem like tiny points of light that have always been there and always will be. Yet stars are not eternal. They are born, they change, and eventually they die. Some live for billions of years, while others burn through their lives much faster. The most massive stars live intense and relatively short lives, and it is these giant stars that eventually give rise to neutron stars. Long before such a star begins shining, it starts as a vast cloud of gas and dust drifting quietly through space. These enormous clouds, known as nebulae, contain mostly hydrogen, the simplest and most abundant element in the universe. Over immense periods of time, gravity slowly pulls parts of the cloud inward. As the material gathers together, the center becomes hotter and denser. Eventually, temperatures rise so high that hydrogen atoms begin to fuse together. This process, called nuclear fusion, releases tremendous amounts of energy. That energy pushes outward while gravity pulls inward. For millions of years, these two forces maintain a delicate balance. Gravity tries to collapse the star, while the energy produced in the core pushes back. This balance allows stars to remain stable for incredibly long periods. Our own sun exists in this balanced state, but stars destined to become neutron stars are far more massive. Some contain 10 or 20 times the mass of the sun. Because they are so large, they burn through their fuel much more rapidly. Their lives are brilliant, but relatively brief. Instead of lasting tens of billions of years, many survive only millions of years, which is surprisingly short on cosmic timescales. Inside these massive stars, the core acts like a giant furnace. Hydrogen gradually transforms into helium. As hydrogen becomes scarce, gravity starts compressing the core once again. Temperatures rise even higher, allowing helium to fuse into heavier elements. Carbon forms, then oxygen, then neon, then silicon. Each stage creates increasingly heavier elements while releasing energy that temporarily supports the star against collapse. This process resembles layers inside an onion. Different elements occupy different regions within the star. The outer layers contain lighter elements, while heavier elements accumulate closer to the center. Over time, the star becomes a complex structure with multiple layers, each participating in its own nuclear reactions. For millions of years, these reactions continue, producing enormous amounts of heat and light. The star shines brilliantly, perhaps appearing blue or white, much brighter than our sun. If such a star existed close to Earth, it would dominate the sky. Fortunately, the nearest examples are safely distant. Eventually, however, the star reaches a critical point. The fusion process creates iron in the central core. Iron is different from lighter elements because fusing iron does not produce useful energy. Instead of supporting the star, iron effectively marks the end of the line. The stellar furnace that maintained balance for millions of years begins to fail. At first, nothing dramatic is visible from the outside. The star still shines. It still appears magnificent. Yet deep inside, the balance that has existed for ages starts to disappear. Gravity, which has patiently waited all this time, begins to gain the upper hand. Without enough energy pushing outward, the core starts collapsing. This collapse happens with astonishing speed. What took millions of years to build can begin falling apart in mere seconds. Matter rushes inward. Temperatures soar. Pressures become unimaginable. Electrons and protons are forced together, creating neutrons in enormous numbers. The collapse accelerates until something remarkable happens. The inner regions become so dense that further compression becomes extremely difficult. The inward rush suddenly halts. Material falling from above crashes into the compressed core and rebounds outward. The result is one of the most powerful explosions in the universe, a supernova. For a brief period, the dying star can outshine billions of other stars combined. Immense amounts of energy spread through space. Shock waves race outward at incredible speeds. Heavy elements forged inside the star are thrown across the galaxy, enriching future generations of stars and planets. The iron in blood, the oxygen we breathe, and many of the atoms making up our bodies were created in stars that lived and died long before the sun existed. In that sense, every human being carries material forged inside ancient stellar furnaces. We are connected to stars in a very real and tangible way. After the explosion, not everything is destroyed. Depending on the original mass of the star, a dense remnant may remain. In some cases, the remaining core becomes a black hole. In others, something equally fascinating survives. A tiny sphere only about 20 kilometers wide, containing more mass than the sun, continues existing in silence. That object is the neutron star. From a peaceful cloud of hydrogen to a brilliant giant, and finally to one of the densest objects in existence, the life of a massive star is both violent and beautiful. Over millions of years, it transforms simple elements into increasingly complex ones, illuminates the galaxy with its light, and ultimately leaves behind a remnant unlike anything found in everyday experience. Somewhere in the Milky Way tonight, countless massive stars are continuing this ancient cycle. Some are young and stable. Others are approaching their final chapters. And hidden among the stars, the remnants of long-dead giants continue their quiet existence, carrying within them the extraordinary conditions that make neutron stars one of the most fascinating objects in the universe. For millions of years, a massive star maintains a delicate balance between two opposing forces. Gravity constantly pulls inward, trying to compress the star, while the tremendous energy produced by nuclear fusion pushes outward. As long as these forces remain evenly matched, the star continues shining peacefully across the darkness of space. Yet this balance is temporary. Eventually, every giant star reaches a point where gravity begins to win. Deep within the center of the star, the supply of fuel gradually becomes exhausted. Layer after layer of nuclear reactions has transformed hydrogen into helium, helium into carbon, carbon into oxygen, and eventually into heavier elements. The final stage produces iron, and iron marks a turning point unlike any other. Unlike lighter elements, iron does not provide the energy necessary to support the star against its own immense weight. The great furnace that sustained the star for millions of years slowly begins to fail. At first, the changes are hidden far beneath the surface. An observer watching from a distant planet would see nothing unusual. The star would still appear bright and stable, yet inside, the core is undergoing a dramatic transformation. Gravity, which has patiently opposed the outward pressure for millions of years, suddenly encounters less resistance. The central regions begin collapsing inward with astonishing speed. The collapse accelerates rapidly. Matter that once occupied thousands of kilometers is compressed into an ever smaller volume. Temperatures rise into the billions of degrees. Pressures become almost impossible to imagine. Atomic nuclei are packed closer together than ever before. Electrons, which normally occupy space around atomic nuclei, are squeezed into protons. Under these extreme conditions, electrons and protons combine, producing neutrons and tiny particles known as neutrinos. This process happens extraordinarily quickly. The entire collapse of the core takes only a fraction of a second. In less time than it takes to blink, a structure larger than Earth is crushed into something roughly the size of a city. Nature performs one of its most astonishing transformations with breathtaking speed. As neutrons accumulate in enormous numbers, the density rises dramatically. Eventually, the matter becomes so compressed that it resists further squeezing. The collapsing core suddenly behaves almost like an incompressible object. Material rushing inward from above slams into this dense center and rebounds outward. A shock wave forms and races through the star. Meanwhile, vast numbers of neutrinos are escaping from the collapsing core. These ghostly particles rarely interact with matter, yet during a supernova, their numbers are so enormous that they play a significant role in transferring energy. Combined with the expanding shock wave, they help drive one of the greatest explosions in the universe. The outer layers of the star are blasted into space at incredible speeds. For a short time, the dying star shines with extraordinary brilliance. A single supernova can release more energy in a few weeks than our sun will produce during its entire lifetime. Across the galaxy, the explosion becomes a beacon visible over unimaginable distances. Ancient observers on Earth occasionally witness these remarkable events. A supernova appearing in the night sky could become so bright that it remained visible even during daylight. Historical records from civilizations in China, the Middle East, and Europe describe mysterious stars that suddenly appeared where none had existed before. These temporary lights were actually the final moments of massive stars reaching the end of their lives. As the explosion expands outward, it carries with it elements forged during the star's lifetime. Carbon, oxygen, silicon, calcium, and many other materials are scattered across interstellar space. Some of the heaviest elements in existence, including gold and platinum, owe their origins to violent stellar events involving neutron stars and supernovae. The atoms making up mountains, oceans, plants, and even human beings were once part of ancient stars that exploded long before the sun was born. After the brilliant display fades, what remains depends largely on the original mass of the star. Extremely massive stars may continue collapsing until they form black holes. Others leave behind something equally extraordinary. The crushed core survives as a neutron star, despite containing more mass than the sun. This newborn object measures only about 20 kilometers across. It rotates rapidly because of a principle familiar to figure skaters. When a skater pulls their arms inward, they spin faster. In a similar way, as the enormous star collapses into a tiny sphere, its rotation speeds up dramatically. A star that once rotated slowly may become an object spinning dozens or even hundreds of times each second. The magnetic field also becomes enormously amplified. The original magnetic field of the giant star is compressed into a much smaller volume, creating magnetic forces billions or even trillions of times stronger than those found on Earth. Some neutron stars possess magnetic fields so powerful that they rank among the strongest known phenomena in the universe. At birth, the surface temperature of a neutron star reaches millions of degrees. Although its diameter is tiny compared with ordinary stars, its intense heat causes it to shine brightly in X-rays and other forms of radiation. Over millions of years, it gradually cools, though it remains extraordinarily hot by human standards. The newborn neutron star now enters a different phase of existence. No longer powered by nuclear fusion, it survives because of the strange properties of matter compressed beyond ordinary understanding. Gravity continues trying to crush it further. while the unusual behavior of densely packed particles provides resistance. The object exists in a remarkable state, balanced between overwhelming collapse and extraordinary pressure. Around it, the expanding debris from the supernova continues traveling through space. Beautiful clouds of glowing gas slowly spread outward over thousands of years, creating structures known as supernova remnants. Some of these remnants can still be observed today. They serve as silent monuments marking the locations where ancient stars ended their lives and neutron stars were born. Across the Milky Way, these explosions have occurred countless times. Every neutron star drifting quietly through space represents the surviving heart of a once magnificent giant. Though the star itself has vanished, its core remains, carrying within it some of the most extreme conditions found anywhere in the universe. The calm and compact sphere left behind contains secrets that challenge our understanding of matter itself, making neutron stars among the most fascinating remnants that nature has ever created. Among all the objects scattered throughout the universe, neutron stars possess one of the most surprising combinations imaginable. They are incredibly small compared with ordinary stars, yet they contain astonishing amounts of matter. A neutron star can hold more mass than our sun, while measuring only about 20 kilometers across. This strange balance between size and mass makes neutron stars unlike almost anything people encounter in daily life. An ordinary experience, large objects usually weigh more than small ones. Mountains contain more material than stones. Oceans contain more water than lakes. Even planets are larger and heavier than moons. The relationship between size and mass feels intuitive because it surrounds us everywhere. Yet neutron stars challenge these familiar expectations in dramatic ways. To appreciate just how unusual they are, consider our sun. The sun has a diameter of nearly 1.5 million kilometers. More than 1 million Earths could fit inside it. Despite its enormous size, much of the sun consists of hot gas spread over a vast volume. A neutron star, by contrast, squeezes a similar amount of mass into an object only about 20 kilometers wide. If the sun could somehow be compressed without changing its mass, the result would resemble a neutron star. The reason for this extraordinary density lies in the collapse that occurred during the star's death. Before the supernova, the giant star possessed layers extending millions of kilometers into space. After the explosion, only the central core survived. Gravity forced this core inward with unimaginable intensity, crushing matter far beyond anything found naturally on Earth. In everyday objects, atoms contain enormous amounts of empty space. The nucleus occupies only a tiny fraction of an atom's total size. Electrons move around the nucleus at relatively large distances. If the nucleus were enlarged to the size of a marble, the electrons would orbit many meters away. Most of the atom consists of emptiness. This hidden emptiness is one reason ordinary matter can be compressed. When pressure is applied to a sponge, air spaces collapse. Under much greater pressures, even atoms themselves can be squeezed closer together. Inside a dying massive star, the force of gravity becomes so overwhelming that it removes nearly all the empty space separating particles. Electrons and protons are pushed together. Neutrons become dominant. Matter enters a state that no longer resembles anything familiar. The resulting material reaches densities so extreme that a single cubic centimeter would weigh hundreds of millions of tons. Numbers like these are difficult to imagine because there are no direct comparisons in human experience. Suppose a sugar cube made from neutron star material could somehow exist safely on Earth. Its weight would exceed that of many mountains. Of course, such material cannot remain stable under ordinary conditions. Removed from the intense gravity of the neutron star, it would behave very differently. Nevertheless, the comparison offers a glimpse into the incredible concentration of matter inside these stellar remnants. Despite their enormous masses, Neutron stars remain surprisingly compact because another remarkable process prevents complete collapse. Gravity constantly attempts to compress the star even further. Left unchecked, it would continue squeezing matter indefinitely. Yet nature provides resistance through the strange behavior of particles under extreme conditions. Neutrons are not ordinary objects like tiny balls stacked together. They are quantum particles governed by rules that differ greatly from everyday intuition. One of these rules prevents identical particles from occupying exactly the same state. As neutrons are forced closer and closer together, this quantum effect generates an immense pressure that opposes gravity. This balance creates a stable object. Gravity pulls inward. Quantum effects push outward. The result is a neutron star, an object suspended between collapse and resistance. It exists in a state unlike anything encountered in normal life. The compact size of neutron stars also produces extraordinary surface gravity. On Earth, gravity gently holds people to the ground. A person weighing 70 kilograms experiences a manageable force. On a neutron star, the same individual would encounter gravity hundreds of billions of times stronger. Such conditions are beyond anything the human body could survive. Even falling objects behave differently near these stars. Something dropped from a small height would strike the surface at incredible speeds. A pebble could release energy comparable to a powerful explosion. The surface itself is so extreme that ordinary concepts of weight and pressure lose much of their familiar meaning. Because neutron stars are small, they also rotate rapidly. Conservation of angular momentum ensures that when the original giant star shrinks dramatically, its rotation speeds up. Much like a spinning ice skater pulling in their arms, the collapsing core accelerates. Some neutron stars complete hundreds of rotations every second. Their surfaces move at significant fractions of the speed of light. Yet, despite their speed and density, neutron stars are surprisingly spheres. The tremendous gravity crushes large mountains and irregular features. Any object sticking too far above the surface experiences forces that quickly flatten it. The difference between the highest peak and the lowest valley may amount to only a few millimeters or centimeters. Compared with Earth, whose mountains rise kilometers above sea level, neutron stars are remarkably uniform. Their compact nature also influences the space around them. According to Einstein's theory of gravity, mass bends space-time. Since neutron stars concentrate enormous masses into tiny volumes, they produce powerful gravitational effects. Time itself flows slightly differently near their surfaces. Light, escaping their gravity, loses energy and shifts toward longer wavelengths. These effects have been measured and provide important tests of our understanding of the universe. Perhaps most remarkable is the fact that neutron stars represent a boundary between two cosmic possibilities. If the surviving core after a supernova contains too little mass, it may become a white dwarf. If it contains too much mass, gravity eventually overwhelms every form of resistance, producing a black hole. Neutron stars occupy the narrow region between these two outcomes, balancing on one of nature's most extraordinary thresholds. Far away in the quiet darkness of the galaxy, countless neutron stars continue existing as compact remnants of ancient explosions. Though no larger than cities, they contain masses greater than the sun. Their small size hides unimaginable density, and their calm appearance conceals some of the most extreme conditions found anywhere in the known universe. Looking at them from afar, one might never suspect that such tiny spheres are among the heaviest and most remarkable objects nature has ever created. Among the many extraordinary features of neutron stars, perhaps nothing is more astonishing than their gravity. Gravity is something people experience constantly, yet rarely notice. It keeps oceans attached to Earth, causes rain to fall, and allows people to walk without floating into the sky. On our planet, gravity feels gentle and familiar. It shapes everyday life so naturally that it often goes unnoticed. But around a neutron star, gravity enters a realm that is almost impossible to compare with anything encountered in ordinary experience. A person standing on Earth experiences an acceleration of about 10 meters per second every second. This force feels normal because humans evolved under these conditions. Mountains remain standing, rivers flow peacefully, and objects dropped from a table fall at predictable speeds. Although gravity governs countless aspects of daily life, it does so quietly. The gravity surrounding a neutron star is anything but quiet. Despite having a diameter of only about 20 kilometers, a neutron star contains more mass than the Sun. This enormous amount of matter concentrated into such a tiny volume creates gravitational forces hundreds of billions of times stronger than those found on Earth. If someone could somehow approach the surface, the difference would be overwhelming. Imagine dropping an object from a height of just 1 meter above the surface of a neutron star. On Earth, it would strike the ground gently after a fraction of a second. Near a neutron star, the same object would accelerate so violently that it could hit with a speed reaching millions of kilometers per hour. Even something as insignificant as a grain of sand could release enormous amounts of energy when it collided with the surface. These conditions make neutron stars among the most dangerous places in the universe. Human bodies, spacecraft, and ordinary materials are not designed to withstand such extreme forces. Long before reaching the surface, tidal forces and radiation would present overwhelming challenges. Fortunately, neutron stars are incredibly distant, existing safely far from our everyday lives. One remarkable consequence of this intense gravity is the shape it imposes on the star itself. On Earth, mountains rise several kilometers above the surrounding landscape. Valleys descend deep below sea level. Continents and oceans create dramatic differences in elevation. A neutron star, however, possesses gravity so strong that even tiny irregularities are suppressed. Any mountain that becomes too tall is gradually crushed under its own weight. Scientists estimate that the tallest features on many neutron stars may be no higher than fractions of a millimeter or perhaps a few centimeters. In other words, some of the smoothest objects in existence are also among the densest. Seen from afar, a neutron star might appear almost perfectly spherical. Gravity also influences the atmosphere. Earth's atmosphere extends upward for hundreds of kilometers, gradually thinning with altitude. Around a neutron star, the atmosphere is astonishingly thin. The immense pull compresses gases into layers sometimes only centimeters thick. What would be considered a vacuum by earthly standards could still count as an atmosphere on a neutron star. Yet, gravity affects more than matter. According to Einstein's theory of general relativity, gravity also influences space and time themselves. Massive objects bend space-time, creating what we perceive as gravitational attraction. Since neutron stars pack tremendous mass into such a small region, they warp space-time in extraordinary ways. One consequence is called gravitational time dilation. Time itself flows differently in strong gravitational fields. Near the surface of a neutron star, clocks run slightly slower compared with clocks far away. To an observer standing at a safe distance, processes occurring near the neutron star appear subtly slowed. This effect is not merely theoretical. Similar phenomena have been measured around Earth using extremely precise clocks. Satellites used for navigation systems must account for these differences. Around neutron stars, the effect becomes much stronger. Time does not stop, but it behaves differently than it does in regions where gravity is weaker. Light is also affected. Normally, light travels away from objects and reaches observers unchanged. Near a neutron star, escaping light must fight against immense gravity. As it climbs away, it loses energy and shifts toward longer wavelengths. This process, known as gravitational redshift, provides scientists with valuable clues about the star's properties. Even more fascinating is the way gravity bends the paths of light rays. On Earth, Looking around a corner is impossible because light travels mostly in straight lines. Around a neutron star, space-time itself curves so strongly that light paths bend noticeably. This means observers can sometimes see regions of the star that would otherwise remain hidden. If someone could safely hover above a neutron star, they might see more than half of its surface at once. Light emitted from the far side would curve around the star, allowing regions normally out of sight to become visible. Such behavior sounds almost magical, yet it follows naturally from Einstein's understanding of gravity. Another consequence involves escape velocity. On Earth, rockets must reach about 11 kilometers per second to overcome gravity completely. Near a neutron star, escape velocities approach a significant fraction of the speed of light. Light itself can still escape, which distinguishes neutron stars from black holes, but doing so requires enormous energy. Despite their incredible gravity, neutron stars do not endlessly collapse. Something remarkable resists further compression. Quantum mechanical effects involving neutrons provide a counterbalance to gravity, maintaining a delicate equilibrium. These opposing forces create one of the most extraordinary states of matter in the universe. Scientists continue studying neutron stars because they offer opportunities to test theories that cannot easily be examined elsewhere. Conditions near these objects allow researchers to explore gravity under circumstances impossible to recreate in laboratories. Each observation helps refine our understanding of how nature behaves at its most extreme, far out among the stars. These compact remnants continue exerting their immense gravitational influence. Invisible and silent to the naked eye, they bend space, alter time, and hold matter together with unimaginable strength. Their gravity represents one of the universe's greatest demonstrations of power, a force so extraordinary that familiar ideas about weight, motion, and even time itself begin to take on entirely new meanings. Everything familiar in everyday life, from the air inside a room to the pages of a book and the stars visible in the night sky, is built from atoms. These tiny structures are so fundamental that they form the basis of nearly all ordinary matter in the universe. Yet inside a neutron star, the conditions become so extraordinary that atoms themselves cannot survive in their usual form. In this strange environment, matter undergoes a transformation unlike anything experienced elsewhere in daily existence. To appreciate what happens inside a neutron star, it helps to begin with something simple. Every atom consists of a central nucleus surrounded by electrons. The nucleus contains protons and neutrons packed closely together, while electrons occupy regions far away from the center. Surprisingly, atoms are mostly empty space. If the nucleus were enlarged to the size of a marble, the surrounding electrons might orbit several meters away. The apparent solidity of everyday objects arises not because atoms are tightly packed spheres, but because of the forces acting between particles. In ordinary circumstances, this arrangement remains stable. Atoms combine to form molecules. Molecules form materials, and these materials build planets, oceans, living creatures, and stars. Even under the immense pressures found deep inside Earth, atoms largely retain their identities. The same is true within the Sun. Although temperatures there are extreme, individual nuclei still exist separately. But the story changes dramatically when a massive star collapses. During the final moments before a neutron star is born, gravity compresses matter with unimaginable intensity. The process occurs so rapidly that atoms are forced closer together faster than they can maintain their ordinary structures. The vast empty spaces inside atoms begin disappearing. The first casualties are the electrons. Under ordinary conditions, electrons occupy distinct energy levels around the nucleus. They are responsible for chemistry, electricity, and many familiar properties of matter. Yet as compression increases, electrons become squeezed into increasingly smaller regions. Eventually, the pressure grows so enormous that their normal arrangement can no longer survive. At this stage, electrons are pushed directly into atomic nuclei. There, they combine with protons through a process called electron capture. A proton and an electron merge, producing a neutron and a tiny particle known as a neutrino. Vast numbers of neutrinos escape into space, carrying away tremendous amounts of energy. As this process continues throughout the collapsing core, more and more protons disappear. Neutrons begin to dominate. Matter gradually changes into something fundamentally different from anything encountered on Earth. The familiar world of atoms and chemistry gives way to an environment controlled by nuclear forces and quantum mechanics. One way to imagine this transformation is to picture a crowded stadium. At first, spectators have plenty of room to move. As more people enter, the available space decreases. Eventually, movement becomes restricted. In the collapse of a massive star, however, the crowding becomes so extreme that the spectators themselves begin changing. Ordinary structures cease to exist, replaced by an entirely new arrangement. The destruction of atomic structure means that chemistry, as humans understand it, effectively ends inside much of a neutron star. There are no molecules, no crystals, no liquids resembling water, and no gases resembling air. Concepts familiar from daily life lose much of their meaning. Matter enters a regime where the rules governing ordinary materials are no longer sufficient. Interestingly, this transformation does not happen all at once. The outermost regions of a neutron star still contain atomic nuclei arranged in unusual patterns. As one travels deeper, conditions become increasingly extreme. Nuclei become richer in neutrons and are packed closer together. Eventually, some neutrons begin escaping from nuclei altogether, creating a strange mixture of nuclei immersed in a sea of free neutrons. Deeper still, the distinction between individual nuclei becomes blurred. Matter enters forms that scientists are still trying to understand. Some theories suggest that bizarre structures resembling sheets, tubes, or clusters may appear. Because their shapes resemble various kinds of pasta, researchers have given them names inspired by food. Although these terms sound playful, they describe serious attempts to understand one of the strangest states of matter in existence. What makes this especially fascinating is that such conditions cannot easily be recreated on Earth. Laboratories can generate enormous pressures and temperatures, but only for tiny fractions of a second and in very small regions. Neutron stars provide natural laboratories where matter has existed under these extraordinary circumstances for millions or even billions of years. The density inside these stars becomes so immense that a single teaspoon of material would weigh billions of tons. Yet despite this incredible compression, matter does not collapse indefinitely. Quantum effects involving neutrons provide resistance, creating a balance between gravity and internal pressure. Without these effects, neutron stars would continue collapsing and might eventually become black holes. Scientists are still uncertain about exactly what forms matter takes deep within neutron stars. Different models predict different possibilities. Some suggest exotic particles may appear. Others propose that even neutrons themselves could break apart into their constituent quarks. The truth remains hidden beneath layers of matter that no human has ever directly observed. Remarkably, the atoms that once existed inside the original massive star had histories stretching back billions of years. Many were forged in earlier generations of stars. During the collapse, those familiar atomic structures were erased, transformed by gravity into something entirely new. In a sense, a neutron star represents one of nature's most radical acts of recycling, taking ordinary matter and reshaping it into forms that challenge human understanding. Far away in the darkness of the galaxy, countless neutron stars continue preserving these extraordinary conditions. Hidden beneath their thin outer surfaces lies matter compressed beyond imagination. Where atoms surrender their identities, and the familiar world gives way to one of the most mysterious realms in the universe. Deep inside these silent remnants, the ordinary building blocks of matter are transformed into something profoundly strange, revealing just how diverse and surprising nature can be when gravity pushes matter to its absolute limits. Although neutron stars are famous for their extraordinary interiors, the journey toward their deepest secrets begins with a surprisingly thin outer layer. Compared with the immense density hidden farther below, the surface and crust of a neutron star might almost seem ordinary. Yet even these outer regions are unlike anything found naturally on Earth. What appears to be a quiet and solid exterior conceals conditions so extreme that familiar materials behave in entirely unexpected ways. From a great distance, a neutron star may look deceptively simple. It is a nearly perfect sphere, only about 20 kilometers across, glowing faintly in X-rays and spinning silently through the darkness of space. But beneath that calm appearance lies a layered structure, and the first part of that structure is the outer crust. If someone could somehow approach a neutron star safely, they would not find oceans, mountains, clouds, or landscapes resembling those on Earth. Instead, they would encounter a surface subjected to gravity so intense that everything is compressed to extraordinary levels. Even the atmosphere above the surface is astonishingly thin. On Earth, our atmosphere stretches upward for hundreds of kilometers. Around a neutron star, the atmosphere may be only a few centimeters thick. This delicate layer contains incredibly hot gases and plasma. Temperatures near young neutron stars can reach millions of degrees. Despite such heat, the tremendous gravity prevents the atmosphere from expanding very far. Everything is pressed downward with overwhelming force, creating one of the thinnest atmospheres known in the universe. Directly beneath this atmosphere lies the solid outer crust. Calling it solid, however, does not fully capture its remarkable nature. The crust consists of tightly packed atomic nuclei, immersed in a sea of free-moving electrons. These nuclei are arranged in crystalline structures, forming what may be one of the strongest materials in existence. On Earth, crystals are familiar. Salt, diamonds, and many minerals possess orderly arrangements of atoms. But the crystals inside a neutron star are subjected to pressures billions of times greater than anything found on our planet. Under these conditions, matter becomes incredibly rigid and resilient. Some scientists believe that neutron star crusts are billions of times stronger than steel. Yet despite this immense strength, the crust itself is surprisingly thin compared with the star as a whole. A neutron star may have a radius of roughly 10 kilometers, while the crust extends only about 1 kilometer beneath the surface. In human terms, it is rather like the skin of an apple compared with the fruit inside. Most of the star's mass lies much deeper, hidden beneath this outer shell. As one descends into the crust, density steadily increases. Near the surface, atomic nuclei still resemble familiar elements such as iron. These nuclei are packed much closer together than on Earth, but they retain much of their identity. The deeper regions, however, become increasingly strange. Gravity squeezes matter so intensely that electrons are forced into higher energy states. Meanwhile, nuclei absorb additional neutrons and become richer in these particles. Their compositions begin drifting away from anything commonly encountered in laboratories. Exotic isotopes appear, many of which cannot survive under ordinary conditions. Imagine descending deeper and deeper into a world where the rules governing chemistry gradually fade away. Elements that would normally be unstable become possible. Atomic nuclei become larger and more neutron-rich. The distinction between familiar substances begins to blur. Matter enters a realm governed by conditions impossible to reproduce completely on Earth. One fascinating aspect of the outer crust is its ability to conduct electricity extremely well. The freely moving electrons create conditions that allow electrical currents to flow with remarkable efficiency. These currents contribute to the powerful magnetic fields observed around neutron stars. In some cases, these magnetic fields become trillions of times stronger than Earth's magnetic field, making neutron stars among the most magnetic objects in the universe. Despite the crushing pressure, the crust is not perfectly static. Over long periods, stresses can build up. Tiny adjustments and fractures may occur, releasing tremendous amounts of energy. These events, known as starquakes, are somewhat analogous to earthquakes on Earth, though vastly more energetic. A slight shift in the crust of a neutron star can produce bursts of radiation detectable across enormous distances. The outer crust also plays an important role in the star's thermal behavior. Heat generated deep within the neutron star slowly travels outward through this region. The crust acts almost like a blanket, influencing how quickly the star cools over millions of years. By observing the temperatures of neutron stars, astronomers can gain clues about the mysterious layers hidden beneath. Even though this region is relatively thin, it represents an important transition between the familiar universe and something far stranger. Above it lies the vacuum of space. Below it lies matter compressed to unimaginable densities. The crust serves as a boundary between ordinary atomic structures and the exotic conditions deeper inside. What makes this even more remarkable is that the crust itself contains more mass than many celestial objects. A single cubic centimeter of material from the deeper parts of the crust would weigh millions of tons. Even the least extreme regions of a neutron star remain far beyond anything humans experience in daily life. Over millions and even billions of years, these crusts endure extraordinary conditions. They survive intense magnetic fields, rapid rotations, and relentless gravitational pressure. Though only about a kilometer thick, they form a resilient shell surrounding one of the strangest interiors in existence. Far beneath this rigid exterior, however, the environment becomes even more unusual. The pressure continues increasing, and eventually some neutrons begin escaping from their nuclei. Matter starts entering a state that scientists had never imagined until the 20th century. The familiar concept of individual atoms gradually disappears, giving way to a landscape where free neutrons and exotic forms of matter begin to dominate. Hidden below the outer crust, the true mysteries of neutron stars slowly begin to reveal themselves. Just below the solid outer crust of a neutron star lies a region where matter begins to behave in ways that seem almost disconnected from ordinary experience. The further one descends beneath the surface, the less familiar the universe becomes. At these depths, the concepts of chemistry, elements, and ordinary solids slowly give way to conditions that challenge even the most advanced theories of physics. The outer crust still contains atomic nuclei, arranged in crystalline patterns. Although these nuclei are squeezed together far more tightly than anything found on Earth, they remain recognizable. Iron, nickel, and other heavy elements continue to exist, though often in unusual forms. But gravity never stops its relentless compression. With every meter deeper into the star, the pressure increases enormously, forcing matter into increasingly exotic states. Eventually, a remarkable threshold is reached. Atomic nuclei become so rich in neutrons and are packed so closely together that some neutrons can no longer remain confined inside them. These neutrons begin leaking out, not violently, but gradually, almost like tiny droplets escaping from an overfilled container. This marks the beginning of the inner crust, one of the strangest environments known in the cosmos. Unlike ordinary solids, which consist of atoms arranged in regular structures, the inner crust contains a bizarre mixture. Atomic nuclei still exist, but they are surrounded by vast numbers of free neutrons moving between them. One might imagine islands of nuclear matter floating within an ocean of wandering particles. The picture is unlike anything encountered in daily life. These free neutrons are not random visitors. They dominate the region. In fact, Much of the matter within the inner crust consists of neutrons no longer attached to nuclei. Their presence creates entirely new physical properties, many of which have fascinated scientists for decades. The densities involved are staggering, even compared with the already extreme conditions near the surface. The inner crust is far denser. A tiny amount of this material would outweigh mountains. Yet, despite the crushing pressure, the matter remains stable, supported by quantum mechanical effects that prevent total collapse. One of the most surprising possibilities within this region is the existence of what researchers sometimes call nuclear pasta. The name sounds amusing, almost out of place in a discussion about stars, but it reflects the strange shapes that matter may assume under these conditions. Normally, atomic nuclei are roughly spherical. However, the competing forces inside the neutron star create a delicate balance between attraction and repulsion. As densities increase, spherical nuclei may begin deforming into elongated rods, flat sheets, hollow tubes, and other unusual structures. Because some of these shapes resemble spaghetti, lasagna, or other pasta forms, scientists adopted playful names to describe them. These structures are not composed of food, of course. They are arrangements of nuclear matter created by extraordinary pressure and density. Their existence remains one of the most fascinating predictions in modern astrophysics. Computer simulations suggest that such patterns could occupy a substantial region deep within neutron stars. What makes these strange structures important is not merely their appearance. Their presence could influence many observable properties of neutron stars. They may affect how heat travels through the star. They may alter magnetic fields. They could influence the vibrations produced during starquakes, and even play a role in the rotational behavior of pulsars. The inner crust may also contain one of the most unusual substances in the universe, a superfluid of neutrons. Under certain conditions, neutrons begin behaving collectively rather than individually. Instead of acting like ordinary particles bouncing randomly, they move together in an organized manner that allows frictionless flow. Superfluidity was first discovered in liquid helium on Earth, but inside neutron stars the phenomenon reaches entirely different scales. Vast oceans of neutrons may flow without resistance through the inner crust. This strange behavior can influence how neutron stars rotate and may explain sudden changes in their spin known as glitches. These glitches have puzzled astronomers for many years. Some neutron stars rotate with astonishing precision, rivaling the accuracy of atomic clocks. Yet occasionally, they experience tiny but measurable increases in rotational speed. The presence of superfluid neutrons beneath the crust provides one possible explanation. Hidden reservoirs of angular momentum may transfer energy to the outer layers, causing the star to spin slightly faster. Despite decades of research, many details remain uncertain. No laboratory on Earth can fully recreate the immense pressures found inside neutron stars. Scientists rely on theoretical calculations, computer simulations, and astronomical observations to piece together what might exist beneath the surface. Every new observation provides clues. Measurements of temperature, magnetic fields, and rotational behavior help researchers test different models. Some theories predict thicker layers of nuclear pasta. Others suggest different compositions or structures. The true nature of the inner crust remains one of the outstanding mysteries in astrophysics. What makes this region especially fascinating is that it represents a transition. Above it lies the outer crust, where recognizable nuclei and electrons dominate. Below it lies an even stranger world, where densities approach those found inside atomic nuclei themselves. In these deeper layers, the distinction between individual nuclei begins to disappear altogether. There, matter enters conditions so extreme that even neutrons themselves may behave in unfamiliar ways. The boundaries separating particles become increasingly blurred, and the forces governing their interactions grow ever more important. The deeper one travels into a neutron star, the further one moves from the ordinary universe and into a realm where nature reveals some of its most remarkable secrets. Hidden beneath the thin surface and the rigid crust, these strange materials remain silently compressed by gravity. Though invisible to the eye and unreachable by human hands, they represent one of the most extraordinary forms of matter known to exist. In the quiet darkness of space, countless neutron stars preserve these mysterious regions, offering a glimpse into a world where the familiar building blocks of reality are transformed into something profoundly strange and beautiful. As the journey continues deeper beneath the surface of a neutron star, the environment becomes increasingly unfamiliar. The orderly crystalline structures of the outer crust gradually fade, and even the bizarre formations of the inner crust begin to give way to something far stranger. Matter is compressed to such incredible densities that many of the concepts people normally use to describe solids and liquids start losing their meaning. In these hidden regions, nature enters one of its most extraordinary realms, a place dominated by vast seas of free neutrons and forms of matter that may exist nowhere else in the universe. On Earth, neutrons are usually found inside atomic nuclei. They live alongside protons and help stabilize atoms. Free neutrons can exist for a short time, but outside nuclei they are unstable and eventually decay. Deep inside a neutron star, however, conditions are completely different. Here, gravity compresses matter so intensely that neutrons become the dominant particles. Instead of being trapped inside individual nuclei, countless neutrons move freely through the star. One might imagine a strange ocean extending beneath the crust, not composed of water, but of particles packed together with unimaginable density. Of course, this is not a liquid in the ordinary sense. It is a state of matter unlike anything found in everyday experience. The neutrons are so crowded that their behavior is controlled by the laws of quantum mechanics rather than familiar ideas about fluids and solids. The densities in this region are truly astonishing. A single cubic centimeter of material from these depths would weigh hundreds of millions of tons. Yet despite this incredible compression, the particles do not simply collapse into one another. Quantum effects create resistance, allowing the neutron star to maintain its structure. Gravity pushes inward relentlessly, while the behavior of the particles provides an opposing force. As scientists study these conditions, they discover that neutrons may not be the only particles present. Although neutrons dominate, small numbers of protons and electrons remain mixed among them. These particles contribute to the electrical and magnetic properties of the star. Their interactions help shape the extraordinary phenomena observed around neutron stars. One particularly fascinating possibility is that the neutrons form a superfluid. In everyday life, liquids experience friction and resistance. Water flowing through a pipe gradually loses energy. Honey moves more slowly because of its viscosity. But a superfluid behaves differently. Once it begins moving, it can flow without losing energy through friction. On Earth, superfluidity has been observed in certain substances cooled to temperatures close to absolute zero. Deep inside neutron stars, however, immense pressure allows superfluidity to exist even at temperatures of millions of degrees. Compared with ordinary standards, these temperatures are incredibly high, yet within the context of neutron star interiors, they are low enough for quantum effects to dominate. This superfluid sea of neutrons behaves in remarkable ways. Instead of rotating like an ordinary liquid, it forms tiny whirlpools called quantized vortices. These microscopic structures allow the superfluid to carry angular momentum. The arrangement and movement of these vortices may explain some of the sudden changes in rotation observed in pulsars. Astronomers have detected mysterious events known as glitches, brief moments when a neutron star unexpectedly spins slightly faster. Although the change is tiny, it can be measured with astonishing precision. One explanation suggests that the superfluid deep inside the star stores rotational energy. Occasionally, some of that energy transfers to the crust, producing the observed increase in spin. The deeper one goes, the more uncertain the picture becomes. At sufficiently high densities, entirely new particles may begin appearing. Some theories suggest the presence of hyperons, exotic particles containing strange quarks. Unlike the protons and neutrons familiar from ordinary matter, these particles are rarely encountered under normal conditions. Their existence inside neutron stars remains one of the many unanswered questions in modern astrophysics. Another possibility involves mesons, particles that could form unusual condensates under extreme pressure. Such states of matter have no counterpart in everyday experience. Their presence could influence the mass, size, and cooling behavior of neutron stars. By comparing observations with theoretical models, scientists hope to determine whether these exotic particles truly exist. The challenge lies in the fact that no one can directly observe these hidden regions. Even the most powerful telescopes cannot see inside a neutron star. Researchers must rely on indirect evidence. They study the star's mass, temperature, rotation, and magnetic field, searching for clues that reveal the nature of the matter buried deep below the surface. Computer simulations have become essential tools in this effort. Supercomputers perform enormous calculations, attempting to recreate the behavior of particles under conditions impossible to reproduce in laboratories. Yet even with modern technology, many uncertainties remain. Different models predict different compositions and structures. The truth remains hidden beneath layers of matter compressed by gravity beyond ordinary imagination. What makes neutron stars so fascinating is that they serve as natural laboratories for extreme physics. Conditions inside them cannot easily be duplicated anywhere else. By studying these distant objects, scientists gain insight into the fundamental forces governing matter itself. Questions that cannot be answered on Earth may find their answers within these compact remnants of ancient stars. There is something quietly remarkable about the idea that deep beneath a surface only 20 kilometers across, entire oceans of free neutrons may exist. These invisible seas, flowing without friction and shaped by quantum laws, occupy a world far removed from human experience. They remind us that the universe contains forms of matter far stranger and more beautiful than anyone once imagined. In the darkness of space, neutron stars continue their silent existence. Their surfaces reveal only a small fraction of their true nature. Hidden below lies a realm where particles move collectively, where strange forms of matter may emerge, and where the ordinary boundaries between solids and liquids begin to disappear. The deeper one descends, the closer one comes to the heart of one of the most mysterious objects in the universe, where matter itself approaches conditions that challenge the limits of human understanding. Between the relatively familiar outer crust and the unimaginable depths of the neutron star's core lies a region that has fascinated scientists for decades. This layer, known as the inner crust, occupies only a small fraction of the star's radius, yet it represents one of the most unusual environments in the universe. Here, ordinary atomic structures begin to disappear. Free neutrons emerge in enormous numbers, and matter enters a strange transitional state, unlike anything found elsewhere in nature. Although the word crust may suggest something simple or solid, the inner crust is anything but ordinary. It is not a rigid shell in the everyday sense. Instead, it is a complex mixture of atomic nuclei, free neutrons, and electrons, all compressed by gravity so intense that familiar concepts gradually lose their meaning. If one could somehow travel downward through the neutron star, the changes would not occur suddenly. The transformation would be gradual, almost peaceful in a sense. Near the upper regions of the crust, nuclei remain relatively recognizable. Iron and other heavy elements dominate. As the pressure increases, however, these nuclei become increasingly rich in neutrons. More and more neutrons are squeezed into them, pushing matter into forms that cannot exist naturally on Earth. Eventually, a remarkable point is reached. the nuclei become so overloaded with neutrons that they can no longer contain them all. Some neutrons escape and begin moving freely between the nuclei. This process is known as neutron drip, and it marks the beginning of the inner crust. The name itself sounds almost poetic. One can imagine tiny streams of neutrons slowly leaking out from crowded nuclei, though the reality is governed by the strange laws of quantum mechanics rather than ordinary fluids. Beyond this threshold, free neutrons become increasingly abundant, eventually outnumbering the particles still locked inside nuclei. This environment resembles no ordinary material. It is neither a conventional solid nor a familiar liquid. Instead, islands of nuclear matter are immersed within an ocean of free neutrons, while electrons move throughout the mixture. The entire structure exists under pressures so enormous that even the strongest materials known on Earth would be crushed instantly. Scientists believe that the inner crust may contain one of the strongest substances in existence. The immense pressure forces matter into extraordinarily stable arrangements. Calculations suggest that the crust of a neutron star may be billions of times stronger than steel. Such incredible strength allows the crust to support stresses that would shatter any earthly material. Yet even this extraordinary structure is not perfectly stable. Over time, rotational changes and magnetic forces can cause stresses to accumulate. Eventually, the crust may crack or shift slightly. These events, known as starquakes, release enormous amounts of energy. Though the physical movement involved may be incredibly small, the resulting bursts of radiation can be detected across vast distances. The inner crust also plays a vital role in regulating the star's rotation. Many neutron stars rotate with astonishing regularity. Some spin dozens or even hundreds of times each second with a precision rivaling the finest clocks ever built. Yet astronomers occasionally observe sudden increases in rotation speed, known as glitches. For years, these glitches puzzled researchers. The leading explanation involves the superfluid neutrons hidden within the inner crust. Because superfluids behave differently from ordinary matter, they can store angular momentum in unusual ways. Under certain conditions, energy can suddenly transfer from the superfluid to the crust, causing the entire star to spin slightly faster. Although these changes are tiny, they are measurable. In fact, some glitches have been observed with extraordinary precision, providing valuable clues about the hidden layers beneath the surface. In a sense, neutron stars occasionally reveal small hints about their interiors through these subtle irregularities. Perhaps one of the most fascinating features of the inner crust is the possible existence of nuclear pasta. As densities continue increasing, ordinary spherical nuclei may become unstable. Competing forces between attraction and repulsion can distort them into bizarre shapes. Some may stretch into long cylinders resembling spaghetti. Others may flatten into sheets reminiscent of lasagna. More complicated structures resembling tubes or tangled networks may also appear. Despite the playful names, these configurations are serious scientific predictions. Computer simulations suggest that such structures may naturally emerge under the extreme conditions found in neutron stars. If they exist, they could influence how heat flows through the star, how magnetic fields evolve, and how vibrations travel through the crust. These strange formations also represent a bridge between two very different worlds. Above them lies matter composed of recognizable nuclei. Below them lies the outer core, where individual nuclei may disappear entirely. The inner crust therefore acts as a transitional region, where the familiar gradually gives way to something profoundly unfamiliar. One remarkable aspect of this region is how inaccessible it remains. No spacecraft can visit it. No sample can be collected. No laboratory on Earth can fully recreate its conditions. Scientists must rely on theory, observation, and computer simulations to uncover its secrets. Every pulse or glitch, every burst of radiation, and every temperature measurement provides another clue in the ongoing effort to understand this hidden realm. Despite all that has been learned, many questions remain unanswered. How thick is the inner crust exactly? What structures dominate its deepest layers? How do magnetic fields interact with the superfluid neutrons? Does nuclear pasta truly exist? Researchers continue searching for answers, and each new observation brings humanity slightly closer to understanding these extraordinary objects. Far beneath the thin atmosphere and rigid surface, the mysterious inner crust quietly endures. It supports unimaginable pressures, contains seas of frictionless neutrons, and may host some of the strangest structures in the cosmos. Hidden from sight and unreachable by any direct means, it remains one of nature's most fascinating creations, a silent boundary between the recognizable world of atomic nuclei and the even stranger depths waiting farther below, where the true heart of the neutron star begins to emerge. Beyond the strange landscapes of the inner crust, the structure of a neutron star begins to change in a far more dramatic way. The boundaries that once separated recognizable atomic nuclei slowly disappear, and matter transitions into a state where individual nuclei no longer exist as distinct objects. This deeper region is known as the outer core, and it represents one of the most extreme environments in the universe, where matter is compressed into forms that challenge even the most advanced theories of physics. In the inner crust, nuclei still persist, even if they are distorted and immersed in a sea of free neutrons. But as pressure continues to increase with depth, those nuclei are gradually squeezed so tightly together that their identities begin to dissolve. The spaces between them vanish completely. At this point, matter becomes a uniform mixture of particles, primarily neutrons, with smaller numbers of protons and electrons scattered throughout. What was once a structured lattice of nuclear islands transforms into something far more uniform. The distinction between individual nuclei fades, and the material becomes a continuous nuclear fluid. This is not a fluid in the everyday sense, like water or air. Instead, it is a dense, quantum-governed medium where particles interact through the strongest forces in nature. The outer core is dominated by neutrons, but protons still play an important role. Even though they are far fewer in number, protons carry electric charge, and their presence allows the formation of extremely powerful magnetic fields. Electrons, although light and sparse compared to neutrons, help maintain electrical neutrality and contribute to the star's overall stability. One of the most fascinating aspects of this region is that matter behaves more like a quantum liquid than a classical substance. In everyday life, liquids have molecules that move randomly but remain distinct. In the outer core, particles are so densely packed that quantum effects dominate their behavior entirely. Their positions and motions are governed not by simple collisions, but by probability and fundamental quantum rules. Despite the extreme compression, the outer core does not collapse further because neutron degeneracy pressure provides resistance. This pressure arises from the quantum mechanical principle that identical particles cannot occupy the same state. As neutrons are forced closer together, this principle creates an opposing force that helps support the star against gravity. Without this effect, the neutron star would collapse into a black hole. Temperatures in the outer core are still extremely high by human standards, often reaching millions of degrees. Yet in the context of neutron star physics, these temperatures are relatively low compared to the energies involved in particle interactions. As a result, many particles behave in highly ordered quantum states rather than chaotic thermal motion. Another remarkable possibility in this region is the existence of neutron superfluidity, extending even deeper than in the inner crust. In such a state, neutrons pair up in ways that allow them to flow without friction. These paired particles move collectively, forming a macroscopic quantum state that extends across large regions of the core. This superfluid behavior has important consequences. It influences how the star rotates, how it cools over time, and how energy is transported through its interior. Because the superfluid can move independently from the crust, differences in rotation between layers can develop. When these differences are suddenly corrected, the result can be the glitches observed in pulsars. The outer core is also a region where protons may form a superconducting state. In superconductors, electrical resistance disappears, allowing currents to flow indefinitely without loss of energy. On Earth, superconductivity requires extremely low temperatures. Inside neutron stars, however, the combination of pressure and quantum interactions allows similar behavior to emerge under completely different conditions. If protons in the outer core truly form a superconductor, the implications are extraordinary. Electrical currents could circulate for extremely long periods, helping sustain the star's intense magnetic field. These currents may be responsible for the stability and long life of neutron star magnetism, which can remain strong for millions or even billions of years. As depth increases within the outer core, matter becomes more uniform and increasingly difficult to describe in familiar terms. There are no atoms, no molecules, and no crystals. Instead, there is a dense mixture of quantum particles interacting through fundamental forces. The behavior of this matter is determined not by classical physics, but by the rules of quantum chromodynamics and many-body quantum theory. Despite decades of study, scientists still do not fully understand the exact composition of the outer core. Different theoretical models predict slightly different arrangements of particles. Some suggest additional exotic particles may appear under certain conditions. Others propose that matter remains primarily composed of neutrons, protons, and electrons in a highly correlated quantum state. The difficulty lies in the fact that these conditions cannot be recreated in laboratories on Earth. Even the most powerful particle accelerators can only briefly reach comparable energies, and never in the same dense, stable environment. As a result, neutron stars remain one of the few natural laboratories where matter exists under such extreme conditions for long periods of time. Observations from astronomy provide indirect clues. By measuring the mass and radius of neutron stars, scientists can infer properties of the outer core. The way neutron stars spin, slow down, and emit radiation also provides valuable information. Each piece of data helps narrow down the possible models of what lies beneath the surface. The outer core therefore represents both a boundary and a gateway. Above it lies the crust, where remnants of atomic structure still exist. Below it lies the deeper interior, where matter may take on even more exotic forms. The outer core stands at the center of this transition, holding the key to understanding how matter behaves under the most extreme conditions found in nature. Hidden far beneath the surface of the neutron star, this region continues its silent existence. It is a place of immense density, powerful quantum effects, and extraordinary stability. Though invisible and unreachable, it plays a fundamental role in shaping the behavior of the entire star, quietly governing the dynamics of one of the universe's most remarkable objects. At the deepest accessible layers of a neutron star, beneath the outer crust and the outer core, lies a region that pushes the boundaries of known physics to their absolute limit. This is the deep core, a place where matter is compressed so intensely that even the familiar descriptions of neutrons, protons, and electrons may no longer fully apply. It is one of the most mysterious environments in the universe, not because we lack imagination, but because nature itself hides its rules under conditions that cannot be recreated anywhere else. As depth increases inside a neutron star, gravity continues its relentless compression. In the outer core, matter is already a dense quantum fluid dominated by neutrons, with a small fraction of protons and electrons mixed in. But in the deep core, densities rise even further, approaching and possibly exceeding the density found inside atomic nuclei. At this point, matter enters a regime where the structure of particles becomes uncertain. One of the central questions about the deep core is whether neutrons remain intact. In normal conditions, neutrons are stable within nuclei, but under extreme pressure, they are forced so closely together that their internal structure may begin to matter. Neutrons and protons are not fundamental particles in the deepest sense. They are made of smaller components called quarks, held together by gluons through a force described by quantum chromodynamics. In the deep core, some theories suggest that neutrons might begin to break down into their constituent quarks. If this happens, matter would transition into a new state often described as quark matter. Instead of individual neutrons and protons, there would be a dense sea of quarks moving freely, still influenced by strong nuclear forces, but no longer confined inside single particles. This idea leads to one of the most fascinating possibilities in astrophysics, the quark core. In this hypothetical region, matter exists in a form even more extreme than nuclear matter. Quarks may roam in a highly interacting fluid, creating conditions unlike anything found in the rest of the universe. Some models suggest this state could be stable inside neutron stars, while others propose it may only appear under certain pressures or masses. Another possibility is that the deep core contains a mixture of exotic particles beyond quarks and neutrons. Hyperons, which are particles containing strange quarks, may appear when densities become sufficiently high. Their presence would change the balance of pressure and energy inside the star, influencing its size and stability. The introduction of such particles would soften the equation of state, potentially allowing the star to compress further. The equation of state is one of the most important concepts in understanding neutron star interiors. It describes how matter behaves under different pressures and densities. In simple terms, it connects how tightly matter is squeezed to how strongly it resists that compression. In the deep core, this relationship becomes highly uncertain, and small changes in particle composition can lead to large differences in the star's overall structure. Despite the uncertainty, one thing is clear: the deep core must support the immense weight of the entire star above it. Every layer, from the crust down to the outer core, presses inward with enormous force. Only the combined effects of quantum mechanics, nuclear interactions, and possibly exotic particle states can prevent complete collapse into a black hole. Temperatures in the deep core remain a subject of study as well. While still extremely high by everyday standards, they are low compared to the energy scales of particle interactions at these densities. As a result, matter in the deep core may behave in highly ordered quantum states rather than chaotic thermal motion. This ordering allows exotic phases of matter to exist in stable configurations over long periods of time. One of the most intriguing ideas is that the deep core could contain color superconductivity, a state in which quarks themselves pair up in ways similar to electrons in conventional superconductors. In this state, the strong force behaves in unusual ways, potentially allowing matter to flow with minimal resistance at the quark level. If such a state exists, it would represent one of the most extreme forms of quantum matter in the universe. Observationally, the deep core remains hidden. No telescope can directly see inside a neutron star. Instead, scientists rely on indirect measurements such as mass, radius, spin behavior, and gravitational wave signals from neutron star collisions. These observations provide clues about how compressible matter is at extreme densities, helping narrow down possible models for the deep interior. When two neutron stars collide, they briefly reveal information about their internal structure. The way they deform, merge, and emit gravitational waves depends strongly on the properties of the deep core. By studying these signals, scientists can test theories about whether quark matter exists, how stiff or soft the interior is, and how close neutron stars are to collapsing into black holes. Even with these tools, the deep core remains one of the least understood regions in astrophysics. Competing models describe very different internal landscapes. Some suggest a smooth transition from neutrons to quark matter. Others propose sharp boundaries between phases. Some even suggest more exotic possibilities that go beyond current theoretical frameworks. What makes the deep core so remarkable is that it represents a frontier where two of the most powerful theories in physics meet: general relativity and quantum chromodynamics. Gravity tries to compress matter to a point of near infinite density, while quantum forces resist and reshape it into new forms. The outcome of this struggle defines the structure of the entire neutron star, far beneath the surface, hidden under kilometers of crushed matter. The deep core continues its silent existence. It is a region where familiar particles may cease to exist in their usual form, where new phases of matter may emerge, and where the true limits of nature are tested continuously. Though unreachable, it remains one of the most important keys to understanding how the universe behaves under its most extreme conditions, holding secrets that may reshape our understanding of matter itself. As we move deeper into the hidden structure of neutron stars, the question becomes more fundamental than ever before. If matter is compressed beyond the level of atomic nuclei, and even beyond the dense nuclear fluid of the outer core, what remains? At the deepest possible densities, does matter still consist of neutrons and protons? Or does it transform into something even more basic, something closer to the building blocks of those particles themselves? To explore this idea, it helps to step back and look at what a neutron actually is. Despite its name, a neutron is not indivisible. It is a composite particle made of smaller constituents called quarks. Inside a neutron, 3 quarks are bound together by gluons, particles that carry the strong nuclear force. The same is true for protons, which also consist of 3 quarks, but with a different combination that gives them positive electric charge. Under normal conditions, quarks are never found in isolation. They are permanently confined inside protons and neutrons. This confinement is one of the most important features of the strong force. No matter how much energy is applied in everyday experiments, quarks remain bound together. Particle accelerators can briefly probe these structures, but they cannot freely release quarks into ordinary space. However, inside a neutron star, conditions are far from ordinary. The densities in the deep core are so extreme that particles are forced into contact at distances far smaller than anything encountered in laboratories. In this environment, it becomes natural to ask whether the boundaries that normally confine quarks might begin to break down. One of the leading possibilities is the existence of quark matter. In this state, neutrons and protons lose their individual identities, and quarks move more freely within a dense interacting medium. This does not mean quarks float around independently like isolated objects in empty space. Instead, they remain strongly interacting, forming a continuous quantum fluid governed by the rules of quantum chromodynamics. If quark matter exists inside neutron stars, it could take several different forms. One possibility is a smooth transition from nuclear matter into quark matter as density increases. Another possibility is a sharp boundary, where a distinct core of quark matter is surrounded by a shell of neutron-rich material. The exact structure depends on conditions that are still not fully understood. There is also the intriguing idea of strange quark matter. In this scenario, quarks of different types, including strange quarks, become energetically favorable at extreme densities. Matter containing a balanced mixture of up, down, and strange quarks might form a stable phase. Some theories even suggest that strange quark matter could be more stable than ordinary nuclear matter under certain conditions, although this remains unproven. If such exotic matter exists inside neutron stars, it would have profound implications. The overall size and mass relationship of neutron stars would change. Their maximum possible mass before collapsing into a black hole might shift. Even their rotational and thermal properties could be affected. Observations of neutron stars in the universe could then serve as indirect evidence for or against these exotic phases. Despite its importance, quark matter remains hypothetical in astrophysical settings. In particle physics experiments on Earth, scientists have created conditions similar to those in the early universe, briefly producing a state called quark-gluon plasma. However, this plasma exists at extremely high temperatures and low densities, quite different from the cold, ultra-dense conditions inside neutron stars. The two states are related but not identical. Inside neutron stars, if quark matter exists, it would likely be cold in temperature terms, but incredibly dense. This combination creates a very different type of quantum system, one where particles are tightly packed, yet still governed by collective quantum behavior. Understanding this regime is one of the major challenges in modern theoretical physics. Another possibility is that quark matter does not appear at all inside neutron stars. Instead, matter might remain in the form of neutrons and protons, perhaps with additional exotic particles like hyperons emerging at high densities. In this case, the core would still be nuclear matter, but in a highly modified and complex state. The difficulty in distinguishing between these possibilities lies in the limitations of observation. We cannot directly see inside neutron stars. Instead, scientists study their global properties. The maximum observed masses of neutron stars, their radii, and their behavior during mergers all provide indirect clues about what might be happening at their centers. When neutron stars collide, the extreme conditions briefly recreate densities even higher than those inside isolated stars. These events produce gravitational waves that carry information about how matter responds to compression. By analyzing these signals, researchers can place constraints on whether quark matter is likely to exist, or whether nuclear matter remains dominant even at the deepest levels. Another important clue comes from cooling behavior. Neutron stars gradually lose heat over time, and the rate at which they cool depends strongly on their internal composition. If quark matter is present, it may alter how neutrinos are produced and emitted from the core. These differences can be compared with astronomical observations to test theoretical models. Even though direct evidence remains uncertain, the possibility of quark matter inside neutron stars continues to be one of the most exciting ideas in astrophysics. It connects the smallest scales of particle physics with the largest and densest objects in the universe. In a sense, neutron stars may serve as natural laboratories where the fundamental building blocks of matter reveal their deepest behavior under conditions impossible to reproduce on Earth. As we continue descending conceptually into the heart of the neutron star, we move closer to a region where the familiar idea of particles begins to dissolve. Whether quarks are freely moving, partially confined, or entirely absent in favor of other exotic forms, the deep interior remains one of the most mysterious and extreme environments known to science. It is a place where matter itself may take on entirely new identities, hidden beneath layers of crushed stellar remnants, waiting for future observations to reveal its true nature. Deep inside a neutron star, matter does not behave like anything familiar from everyday experience. It is not solid in the usual sense, and it is not liquid in the way water flows through a river. Instead, it exists in exotic quantum states that stretch the limits of what matter can do. Among the most important of these states are superfluidity and superconductivity, two phenomena that become especially powerful under the extreme conditions found in neutron stars. On Earth, superfluidity and superconductivity are rare and fragile effects. They appear only under very low temperatures, often close to absolute zero. In laboratories, scientists have observed superfluids in liquid helium and superconductors in carefully prepared materials. These states are unusual because they remove resistance from motion. In a superfluid, a liquid can flow without friction. In a superconductor, electric current can travel without losing energy. Inside a neutron star, however, the situation is completely different. Instead of relying only on low temperatures, the combination of immense pressure and quantum interactions allows these states to exist in much larger and more stable forms. Even though neutron star interiors can reach temperatures of millions of degrees, the density is so extreme that quantum effects dominate, enabling superfluid and superconducting behavior. One of the most important superfluid components inside neutron stars is the neutron superfluid. In regions such as the inner crust and outer core, neutrons can pair up in correlated states. These pairs behave collectively, forming a fluid that flows without viscosity. Once set in motion, this superfluid can continue moving without losing energy to friction. This behavior leads to one of the most fascinating consequences in astrophysics. A neutron star is not a single rigid object. Instead, it contains multiple layers that can rotate differently. The crust may rotate at one speed, while the superfluid interior rotates at another. This difference creates tension between layers, which can build up over long periods of time. Within the superfluid, rotation is not smooth like a spinning solid object. Instead, it occurs through tiny quantized vortices. Each vortex carries a small amount of angular momentum, and together they form a structured pattern that represents the overall rotation of the fluid. These vortices can move, interact, and rearrange themselves under changing conditions. Sometimes, the vortices become temporarily pinned to structures in the crust or inner crust region. When this happens, the superfluid and crust can become partially decoupled in their rotation. Over time, stress builds up between these layers. Eventually, the vortices suddenly shift, transferring angular momentum to the crust in a rapid burst. This process is believed to be one of the main explanations for pulsar glitches, sudden increases in the rotation speed of neutron stars. Although the change is extremely small, it can be measured with incredible precision by radio telescopes. These glitches provide rare glimpses into the hidden interior of neutron stars, revealing the presence of superfluid behavior deep beneath the surface. Alongside neutron superfluidity, another remarkable phenomenon may occur in the outer core. Protons, although much less numerous than neutrons, can form a superconducting state. In this state, electrical currents flow without resistance. Once established, these currents can persist for extremely long periods without decay. The presence of superconducting protons has important implications for the magnetic field of neutron stars. These stars are known for having some of the strongest magnetic fields in the universe. In certain cases, the field strength can be trillions of times greater than Earth's magnetic field. Maintaining such fields over long timescales requires a mechanism that prevents rapid decay, and superconductivity provides a natural explanation. In a superconducting region, magnetic fields do not simply pass through freely. Instead, they become organized into structures known as flux tubes. These tubes concentrate magnetic field lines into narrow channels that can move and interact with the surrounding matter. The interaction between flux tubes and neutron superfluid vortices creates a complex internal dynamic that influences the star's rotation and magnetic evolution. This interplay between superfluidity and superconductivity makes the interior of a neutron star an incredibly rich and active system. Even though it may appear quiet from the outside, the inside is constantly evolving at the quantum level. Vortices shift, flux tubes move, and angular momentum is redistributed across layers separated by extreme density differences. Another important consequence of these quantum states is their effect on cooling. Neutron stars gradually lose heat over time, primarily through the emission of neutrinos from their interiors. The presence of superfluids and superconductors changes how efficiently these neutrinos are produced. This, in turn, affects how quickly the star cools, which can be observed indirectly through its surface temperature. Different neutron stars appear to cool at different rates, suggesting variations in their internal composition. Some may contain extensive superfluid regions, while others may have different particle arrangements or even exotic cores. By comparing observations with theoretical models, scientists can begin to narrow down the possibilities. Despite significant progress, many questions remain unanswered. The exact pairing mechanisms that allow neutrons and protons to become superfluid or superconducting are still under investigation. The influence of extreme magnetic fields on these states is not fully understood. Even the size and distribution of these regions inside neutron stars are subjects of ongoing research. What makes this area so fascinating is that it connects microscopic quantum physics with macroscopic astrophysical behavior. The motion of tiny vortices and flux tubes inside a neutron star can influence the rotation of an object kilometers wide and more massive than the Sun. Few places in the universe demonstrate such a direct link between the quantum world and cosmic scale phenomena. Hidden beneath layers of crust and dense nuclear matter, superfluids and superconductors quietly shape the behavior of neutron stars. They help regulate rotation, sustain magnetic fields, and control thermal evolution. Although invisible to direct observation, their presence is revealed through subtle signals that travel across the universe, offering rare insights into the extraordinary physics operating inside one of nature's most extreme environments. At first thought, a neutron star sounds like a place where towering mountains might exist, perhaps even larger than anything on Earth. After all, it is a massive object with powerful gravity and a solid crust. But the reality is far more surprising. On neutron stars, mountains do not rise into the sky. Instead, they are crushed into shapes so small that they are almost impossible to imagine. In many cases, what we would call a mountain there may be no larger than a grain of sand, or even smaller. To understand why, it is important to remember the strength of gravity on a neutron star. Even though the star itself is only about 20 kilometers across, it contains more mass than the Sun. This creates a surface gravity so intense that anything sticking up even slightly above the surrounding crust is pulled downward with enormous force. The material simply cannot support tall structures. On Earth, mountains like Everest can rise nearly 9 kilometers above sea level because rock, although heavy, is strong enough to resist Earth's gravity. The crust of Earth is rigid, but it is also relatively weak compared with the forces it must support. On a neutron star, however, gravity is billions of times stronger. The same kind of rock would be instantly flattened. The outer crust of a neutron star is already one of the strongest materials known in the universe. It is made of tightly packed atomic nuclei held together by extreme pressure. Yet even this incredibly strong structure has limits. If a bump or irregularity becomes too large, gravity forces it to collapse until it reaches a stable equilibrium. That equilibrium happens at an astonishingly small scale. Scientists estimate that the tallest possible mountains on many neutron stars may be no higher than a few millimeters, or in some cases even less. This is because the crust cannot support large differences in height without breaking or flowing. Any material that rises too far above the surrounding surface is pulled back down almost immediately. This leads to a strange and almost poetic image. A neutron star is not a rugged world filled with dramatic landscapes. Instead, it is one of the smoothest large objects in the universe. From a distance, it would appear nearly perfectly spherical. There are no oceans, no continents, no valleys, and no towering peaks. Only a thin, compressed crust that is incredibly uniform on large scales. Yet even though these structures are tiny, they are still interesting. The term mountain is used loosely, but these small irregularities can still affect the star in meaningful ways. Even a deformation of a few centimeters can influence rotation, magnetic fields, and radiation emission. In the context of neutron stars, small changes can have large consequences. One reason for this sensitivity is the extreme rotation of many neutron stars. Some of them spin hundreds of times per second. At such speeds, Even tiny bumps on the surface can create detectable variations in emitted radiation. These variations are observed as periodic pulses, which is why many neutron stars are also called pulsars. The smoothness of neutron stars also connects to the strength of their crust. While it is incredibly rigid, it is not perfectly unchanging. Over time, stresses build up due to rotation, magnetic forces, and internal processes. When these stresses exceed a certain limit,